Hello and welcome to Unit 11, Day 5. So we're going to review everything we learned up to this point in Unit 11, which encompasses pretty much everything we've learned in this course. So we're talking about these functions. We're comparing these linear, these exponential, and quadratics. So of these first 6 graphs, which ones are linear? Linear being this y equals mx plus b. Linear being that straight line. Well, if we know it's that straight line, then that is number 3 and number 6. Okay, which ones are exponential? Exponential being that growth function, that decay function. That's that y equals ab to the x. Again, when b is greater than 1, it's a growth. When b is less than 1, it's a decay. Well, I'm seeing that on these graphs, number 1, we see as this growth function, so that's my exponential. And then I'm seeing that this is going to be, it's kind of like a growth, but remember when it was reflected, that negative, it's a little bit weird, but it's still going to have that same curve, that same shape. So that again is going to be an exponential. Okay, our quadratic, remember, is going to be that x squared piece. So as we start looking at this ax squared plus bx plus c, which one has that parabolic, that parabola shape, meaning that happy face, that frowny face? Which one of those have that quadratic? And that is number 2 and number 4. Remember that if it's pointing down, then we know our A is going to be a negative. If it's a happy face pointing up, then we know that our A is a positive. Happy people smile, frowny people frowning, negatives. Cool. Good job. All right, let's take a look at these equations then. So I'm seeing these equations on 7 through 12. We got to figure out which ones are linear, which ones are exponential, and which ones are quadratic. So again, thinking back, we know that our linear is a plain x term. And I see that this one is a plain x. There's nothing with the x. So on number 10, we know it's linear. On number 8, we also see it is a plain x. Yes, it's an up 1 over 3 starting at 4, but that x piece is not having anything done to it with a square or a cubic or anything like that. So that's our linear. Okay, exponentials are called exponentials, because the x is in the exponent. So of these equations, which one has an x as its exponent? And that's going to be number 9. The x is in the exponent. And number 11, the x is in the exponent. Okay, next up we have quadratic. We know our quadratic functions are those x squared pieces. So the things that have those square terms, those quadratics, those parabolas, those are going to be our quadratic, our squares. So I see definitely number 12, quadratic. And then on number 7, we can absolutely have x minus 1 times x minus 1. If you box that, distribute to 3, you would get that 3x squared. So again, that one's going to be our quadratic function. Excellent job. Woo! Okay. So that is 7 through 12. Now, let's take a look at 13, 14, 15. So these are our tables. So what I'm going to do is I'm just going to go ahead and graph them just to get me started. So on number 13, we see that we're going to be at -2 is right above the line. -1 is still right above the line. 0 is at 1. 1 is at 2. 2 is at 4. So I'm seeing that it's shooting up pretty quick. That right there tells us that that's exponential. Okay, another way to look at it. What is the pattern that's happening right here? Are we adding? Are we multiplying? Is it symmetric? What's happening? And I'm saying that for each time it's doubling. It's times 2. And if it's timesing by 2, then we know that it's that exponential double. So our b would be a 2 value. Excellent. So either way, we know it's exponential because it's timesing by 2, or if you take a look at the graph. All right, number 14. So on number 14, we see that -4 is +4. We see -2 is -2 down here. -1 is -2, and 1 is +4. So we see that it's kind of doing something like that, a little bit off. Oh, 1 was 4, sorry, over here. So it has a little bit more symmetry. So as we're starting to work through those, make sure that we're following those patterns, seeing what's happening. On that one, we do see that vertex appearing right here at that -1.5. So I know if it has that middle, if it has that pattern, that's going to be my quadratic function. Okay, number 15. So on number 15, we're going to say, all right, well, let's go take a graph. So on number 15, I'm going to say, okay, this is going to be 1 is 1. Oh, let me slide that line up then. So we know that 1 is 1. Boom. And 3 is -3. 5 is -7. 7 is -11. 9 is -15. And if we go to graph that, we're like, oh, it makes a straight line. Cool. How else could we have known that? Well, I'm seeing that I'm going down 4 and up 2, down 4, and up 2, down 4, up 2, down 4, up 2. So down 4, up over 2 is going to give us a slope of -2. Well, if you have a slope of -2 that's consistent, then you have a linear function. Excellent job, guys. All right, let's take a look at number 16. So 16, 17, and 18 are all going to have these different graphs already graphed, but you've got to tell me all of the different pieces to the puzzle. So I know on number 16 that we have this graph, and because it is going off, then we know that these are really arrows on the edges because that line is going off the graph. If we know that they're arrows, I know that this arrow in the x direction, remember -1, -2, -3, -4, -5, oh, that's -infinity. I also know, though, that that arrow is going up, and up is a y direction. +1, +2, +3, +4, +5, +6, +7, positive infinity. So that one arrow tells us that in the x direction, you're going to -infinity, but in the y direction, you're going to positive infinity. All right, well, what's happening on the other side? I know that this arrow is going out, and that's an x. +1, +2, +3, +4, +5, +6, positive x's. Now, here's the problem, though. That graph is getting pretty flat, which tells me that I have this asymptote thing. Yep, an asymptote. Remember those? And that asymptote is sitting there at y equals -1. So this arrow can't go past that y equals -1. So it can't go to -infinity. It can't even actually get to -1. So this arrow is trying to get to -1. Cool. Okay. So let's talk domain. Now, when we're talking domain, we know that those are our x values. So let's look at all of my x values. On the left, what is my furthest most x value? And I see my furthest most x value is that -infinity. On the right, I see that this furthest most x value on the right-hand side, my biggest x value is going to be that positive infinity. That's what happens with arrows. When you have arrows, they go on forever and ever and ever and ever. All right, the range. The range is our y values. So we need to figure out where is my lowest y value, where is my highest y value. Well, I know my lowest y value is this dotted line. We've already talked about this. We talked about how it's the asymptote. If that's the asymptote, you can't get to it, but you're trying to get super duper close. So how do we show that we're getting close to it without actually reaching it? We use a parenthesis. So we're going to say parenthesis, -1, comma, well, what is my highest most y value? My highest most y value is going to be way up here. And that is a positive infinity. Excellent. All right, let's look at our x-intercept. Remember, our x-intercept is going to be where it crosses the x-axis. So I see my x-axis is sitting here, and it's going to cross right there when x is a positive 1. So my x-intercept is positive 1, 0. Remember, we write x and y-intercepts as points. Okay, likewise, our y-intercept is where it crosses the y-axis. Well, it crosses the y-axis right there when y is positive 1. So again, my y value is going to be positive 1, and the x is 0. Awesome. Maximum and minimum. We need to figure out what is the maximum, the biggest number that we use. Well, we know our biggest number we're trying to use is that positive infinity, meaning it's going on forever and ever and ever, and it's going to keep going and keep going and keep going. If it's going to keep going, do you have a maximum? No, you don't. So for my maximum, there's not one. Well, let's talk minimum. Our lowest y value is trying to get to the -1 asymptote. But can you actually get to the asymptote? No, because you're just going to keep getting closer and closer and closer and closer and smaller and smaller and smaller decimals, but you're not actually going to get there. That's what an asymptote is by definition. So if you can't actually get there, do you have a minimum? Nope. So my max and my min are none. Awesome. Okay. All right. We have our interval of increase and our interval of decrease. So when we are increasing, our graph is going up. When we are decreasing, our graph is going down. So I'm saying as we go across the graph, we're going down, 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 and we're just going to keep going down, 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 closer and closer to that asymptote. So this entire graph is going down, which means that this entire graph is decreasing. So don't get tricked. What's the interval of increase? Correct. You don't have one. The whole thing is decreasing. If that entire graph is decreasing, where is it decreasing? Everywhere. What is everywhere? Negative infinity to positive infinity. Okay, cool. Lovely. All right, end behavior. Now, if you've labeled the graphs like I did at the very beginning, this should be pretty easy. When x is positive infinity, well, my x is positive infinity right over here. And what are we trying to get to? We are trying to get to the asymptote. So my y value is trying to get to the -1. Awesome. Well, when x is negative infinity, so when x is negative infinity, where is your y value trying to get? It's trying to get to positive infinity. It's trying to go up. Another way to look at that, on the right side, the y is going to the asymptote. On the left side, the y is going up. So if that helps. Okay, awesome. All right, average rate of change. Ooh, this is a fun one. So I know that my average rate of change is this rise over run thing. It's also that y2 minus y1 over x2 minus x1. Because I have a graph, I'm just going to do my rise over run. I may do it later with some other stuff just to show us, but I'm just going to do my rise over run to help me think. So I know we have -1 and a 0. So -1 is there, and x of 0 is here. So I'm going to go down 2 over 1. And I know that that's going to be down 2 over 1 or -2. Excellent. Same thing on the next one. We're going to start at 0 and stop at 1. Well, 0 is there, 1 is there. Down 1 over 1. Again, down 1 over 1, -1. Please notice, this exponential function does not have a constant rate of change. It does not. That rate of change, that average rate of change, is different because it doesn't have the same slope. It may be halving, it may be tripling, it may be doubling, whatever it is, it's not going to have the same average rate of change. What it does have on decreasing functions, remember that whole decreasing thing, your average rate of change will always be negative because the graph is decreasing. Okay, excellent job, guys. We're going to pause here and pick back up on number 17 in the next video. Thanks, guys.